Okay, welcome to a short video about exponential functions and specifically natural log e. So let's check this out. It should be some kind of natural decay rate. Fast. Getting slower. And done. Okay, so let's go through an explanation of what Euler's number is and why it's so useful in so many different situations. So let's start with a situation which I think most people can understand and realize the importance of, and that's...
First of all, congratulations, Mr. Krabs.
Hello, I like money.
What inspired you to build a second Krusty Krab right next door to the original?
Money.
Money. So you got some money in the bank, right? You put £1 in the bank and the bank manager says, we can give you 100% interest. Well, it's never going to happen, but let's just say they give you 100% interest at the end of each year. So you put £1 in at the beginning of the year, you would get 100% of £1 added onto your original pound at the end of the year. You get £2. And you think, okay, that's pretty good. Well, it's pretty amazing if you can get that interest rate. But you think, actually, I might be able to get a better deal here. Why are you only calculating the interest once a year? What would happen if you calculated the interest twice a year? So you think you get 100% twice a year. Well, the bank manager's not going to let you get away with that. The bank manager's going to say, what we'll do is we'll give you 50% at 6 months on your original sum, and then we'll give you 50% again. Well, that's what you get in this twice per year scenario. You put £1 in, you get your 50% added on at 6 months, halfway through the year. So now you have £1.50. And then you're going to take another 50% of £1.50 and add that on. And 50% of £1.50 is half of £1.50, 75p. You add that on, you get £2.25. So you are onto a winner, really. So you think, oh, well, let's do this more often. What about 4 times a year? You start with £1. You get 25% of, which is a quarter of 100%, 4 times a year. So you get £1.25, which then, if you take 25% of £1.25 and add it on, you get to £1.56, £1.56 and 0.25 of a penny. The next step would be £1.95 and £2.44 and so on. So what's actually going on, right? Well, initially, you did 1.5 once and then again. So you took your original sum, 1, and you said, I want to add 50% to it. So that's the same as multiplying it by 1.5. And then you took that number and you multiplied it by 1.5 again. So it's really the same as just saying 1.5 squared. When we did the value for 4 times in the year, we did our original value of 1. We multiplied it by 1.25, by 1.25, by 1.25, by 1.25. We did it 4 times. So really we raised 1.25 to the power of 4. So that gets us to thinking, right? I'm thinking, as I go down, I make more and more money.
Money.
What would happen if I could do this many more times? So if I look at this equation, or if I look at what I've actually done, 1.25 to the power of 4, is kind of the same as, or it's exactly the same as doing 1 plus 1 over the number of times I'm taking the interest, right? All raised to the power of the number of times I'm taking the number of steps I've put into this thing, the number of times I'm going to take the interest. As you can see, it becomes 1 plus 1 over 4, which is 1.25, raised to the power of 4, which is the same as what we had here. So then, of course, the question is, well, what happens if we get infinity times? Surely I'd make infinity money.
Money.
Well, if you try doing 1 plus 1 over 100, which is taking interest 100 times a year, but it's 1/100th of the interest, right? The value you get if you plug this into a calculator is 2.70481. If you do it 1,000 times a year, so you have 1,000 divisions in the year, and you raise it to the power of 1,000, you get 2.71692. If you do it to 10,000, 2.718459. And essentially what you find is that as you step up the number n in this equation, you make it larger and larger and larger, you get closer and closer to this value e. which is 2.7182818. It's actually an irrational number. You cannot ever get to the end, or no one has ever discovered a point whereby this number repeats itself. So it's a very interesting and magical number. So having discussed all that, now let's just go back a step and think back about money again.
Money!
Let's just say the bank manager, we live in the real world, and the bank manager is, no, we don't live in the real world. The bank manager offers us 50% a year interest, which is loads of money still. Okay, so now I'm thinking, okay, I get 50% a year. That means if I just calculated interest once a year, so that would be after a year, I'd have £1.50. What would happen if I did it twice a year? Well, I would get 50% at the end of the year, so I would get 25% twice a year. So I'd get £1.25 the first time, and then I'd get 1.25 of £1.25 the second time, which is 1.5625. But I recognise this number. Let's just go back to, here we are, 50, here we go. See, the guy spotted it over here. That's the same as halfway through a year at 100%. So 50% at the end of 1 year is the same as halfway through a year at 100%. What does this mean? Well, let's say we take, so if once 1.25 to the power of 4 gave us 100%, 1 times 1.25 times 1.25 times 1.25 times 1.25, there's the 4. To get 0.5 or 50% would be 1 times 1.25 times 1.25. We've only done this step twice. So we could take this 1.25 to the power of 4, and we could multiply the power of 4 by a half to get what it would be like to get 50% a year. Okay, and this value here, 1.25 to the power of 4, we're going to call crude E. That would be as though we didn't have an infinite number of steps. That would be as though rate was very grainy, okay? But we could use our nice and smooth E, okay? Our nice and smooth E is as though we did this 1,000,000 times a year. So, or an infinite times a year. So now we can start thinking of this as, if I want to count along 2 years at 50% in crude E, this is what I would do. I'd do 1.25 times 1.25, that's the first year. Then I would do 1.25 times 1.25 again, multiplied by the original sum, to get the second year. I get back to the original 2.44. We should recognise from what happens when you do 100% over 1 year. Okay, where am I? Yes, here, sorry. Okay, so if you do it with fancy E, you say I want 50% times the time period. Okay, so what we end up having is this fancy E can work in an equation that sort of operates like this. Let's stick an equal sign at the front. What you're calculating is what you're going to get. You put in before it what you have. So let's say I have £1. I could put that there. Then you multiply by E raised to the power of, and we're going to call the 0.5 in the previous case is the amount lost or gained in a time period n, for instance 2 days. So when we're saying 50%, you're gaining 50% of the original value, what you have. Okay, and the time period is what we're going to put in here, t, number of n that have passed. So if n was 2 days, then if 4 days had passed, then t would be 2, because we're counting in those time periods. So you end up with this pretty neat equation, right? I've put it here as what you get equals what you have multiplied by e raised to the power of kt. But often you'll see it like this. The amount at time t is equal to the amount at initially multiplied by e to the power of kt. Now you can do this for growth or for decay. Okay, so the example at the beginning of the video was the decay one, and we'll have a look at that in a bit more detail now. So again, here we see the bottle emptying, and you should notice that the initial rate of emptying is very, very fast, and then it actually slows down and begins to level off. That's because sort of mechanically you can think of a great deal of pressure pushing the water out at the beginning, and that pressure dropping off as the bottle empties. So the rate at which it empties really depends on how full it is. And we find this in nature in a lot of different scenarios, for instance discharging capacitors or even charging them, or growth of bacteria, or or growth of unimpeded populations, you get similar types of curves. Okay, so let's have a look at that equation we were looking at. So we had the amount at time we're looking at should be equal to the amount at 0 multiplied by e raised to the power of kt. Now I've actually got the data from the water bottle experiment I did, and what I'm going to do is attempt to find out the constant k, right? So k is what I'm looking for. So if I just pick any two random volumes, so the amount at t0 was 10, because on my scale, on my bottle, I actually label it 10, 9, 8, and these are all equidistant, so 10 would be like the volume at the beginning, 10. So A0 would be 10. Okay, and the amount I'm going to look at is how much time did it take to get to 5. That will be A at time, 5, should be equal to e raised to the power of k, and then if I get t off my table, it was 7.85 seconds. So now I can actually do some magic to this, well, I say magic, do some maths to this formula to get k, the constant. Okay, so the first thing I'll do is divide both sides by 10, so I get e to the k 7.85. Okay, and then if I take natural log of both sides, ln 5 over 10 should be equal to, well, that gets rid of the e, cancels the e off, and I just bring down the power k 7.85. And again, to get k on its own, divide both sides by 7.85, and that cancels 7.85 here, so I can calculate k. Now, on the calculator, I'm just going to do, well, 5 divided by 10 is 0.5, so I'll just do ln 0.5, then divide by 7.85, and I get a value for k of minus 0.088. Okay, I'm not going to bother with any units or anything, it's a constant I'm going to use. So this is the constant for this graph. So what this should allow me to do then is to take this formula, the amount at the time I'm looking for, the amount at the beginning, e to the power of kt, and now that I know k, I can stick in any value for t and should be able to predict the amount left. So let's try doing a prediction. How much of the liquid will be around at, say, t equals let's say 15 seconds. Okay, so we'll see how close it is compared to our real values. So if I make t equal to 15 seconds, then the amount at time here will be equal to a at the beginning, which was 10, times e raised to the power of k, which I've just worked out, 0.088, multiplied by the time, which is 15 seconds. Okay, so if I just crunch through on here, and again I want you to look at the calculator here because it's quite easy to make mistakes here. First I'm going to do minus 0.088 and multiply that by 15. Okay, I'll do that first so that I don't make any BODMAS errors, and then I'm going to use e, and it's already raised to the power on this calculator. E answer gives me the value of e raised to the power of these two values, and then multiply by 10 gets me a volume or amount at time 15, AT, will be equal to 2.67. Okay, and on my my thing here, it comes out at at 15 seconds. Well, I've got a value for 15.37 seconds, and it was 2, right? So it's very close to the value we expected. So here you see the formula being used in a real example. The way I would describe it as, if you're familiar with taking the gradient of a graph, so let's, for instance, you're familiar with the concept of Hooke's law. If you determine the constant of the spring, you can then know the extension of the spring for any value. Well, in this, you find the constant of the exponent, and then you can use, it's almost like finding the gradient of a graph, really, and then you can use it to sort of to pick values and discover the amount of something at any other position. We're going to look at a few other examples for bacteria and for radioactive decay, but I'll do those screen captured. Okay, I'll do. Yeah, stop. Okay, so let's have a quick look at some more calculations. So this is a radioactivity question, which you'll be familiar with from GCSE. So at GCSE, you just had to know that things decayed, and that, let's say it took 2 days to get to halfway, right? It would take a further I've drawn it pretty badly, but a further 2 days to get to half of that again, right? Or a quarter of the way from the beginning. Now you can do calculations with how much will be left, sort of using this kind of method, just halving and halving again and halving again each time the half-life passes. But to get specific values, you have to use the method we're going to show you right now. So pause the video and read the question if you haven't already. I'm assuming you've done that. But basically, so we're being told get the time constant for half-life for carbon-14, okay, for its decay. So it takes 5,740 years to half. Okay, so if I get my formula that we've been using throughout, the amount at a given time will be equal to the amount at time 0, all multiplied by the power e raised to the power of the constant times time. So actually, I have t. I know E, obviously. I know A naught, and I know AT. Okay. Well, I'll show you what those are. So the amount at time is going to be a half. The amount at the beginning will be 1, because it's the time it took to half. So whatever the value was, 1.5 is going to suffice for that. E is the value we know. K is what we need to find, and T is 5740. Okay, so I don't really need to divide both sides by 1, because 1 multiplied by anything is just whatever it was, so that 1 doesn't really mean anything. So I'm just going to now do ln of both sides. So it becomes ln 0.5. That means that the power gets brought down and the E disappears, so we end up with K 5740. And then dividing both sides by 5740 cancels this, and I'm just going to get K. So plugging the numbers into the calculator, ln of 0.5 divided by 5740 gives us a value which is negative, which is really important you don't forget, 1.21 times 10 to the minus 4. Okay, to the minus 4, which is the correct answer, 1.2 times 10 to the minus 4. Okay. Okay, so next it says, a piece of wood taken from an axe handle found at the archaeological site has 0.375 times the amount of carbon-14 an equal mass of living wood would have. So now what we're actually, so now it says calculate the age in years. So now what we're actually being given is AT, the amount at given time. A naught in this case would be 1 times obviously EKT, and we have K, so we can find T. So let's sub all our values in. I'm trying to find AT, so I don't really need to do any rearranging here. Amount at the beginning was 1. Okay, the amount at the beginning was 1. Sorry, the amount I've actually got is 80. The amount at this time that I'm trying to find for is 0.375. That's correct. Times E raised to the power of our constant minus 1.21 times 10 to the minus 4 times by our time. Right, so our time is the thing we're trying to find. Again, the 1 can just be ignored. If I do ln of both sides, ln 0.375 will equal, that gets rid of the E, it just becomes minus 1.2 times 10 to the minus 4 times T. Okay, and then simply dividing both sides by 1.2 times 10 to the minus 4, so minus 1.21 times 10 to the minus 4, gets rid of it there, and that will give me T. Okay, so dividing through ln 0.375 divided by minus 1.21 times 10 to the minus 4 gives me a value of 8122, which is the number of years old this sample is. So now we're going to look at another example, which is a biological example. Again, pause the question and have a read, maybe have a try. Okay, so if you've had a read of this question, you'll recognize that you are given a amount at time 0, and then you're told that a time of 1 hour passes, and then you've got the amount at that time, 600. And then you're asked to calculate how much you'll have after 24 hours. We're just going to focus on the first 3 things I underlined first, because we need to get the constant for this reaction, or this rate. So we're going to start with our formula. Amount at time that we're calculating should be equal to the amount at time 0 multiplied by e to the power of kt. Okay, and we just need to find k. Right, so let's go after k. 600 is what we had after the time period t. We started with 200, the amount at time 0, multiplied by e to the k, and the time was just 1 hour. So we can just ignore that one. Okay, rearrange to get e on its own. 600 over 200, which is actually the same as 3, will be equal to e and k, e to the power of k, basically. Okay, so now to get the k down, I just need to take ln of both sides. So ln 3 will be equal to just k. And if you calculate ln 3, you get 1.0986. And notice this time it's a positive value. It's because it's a growth rate. So now I want to use that to get me the amount at 24 hours. So I've got the constant, and I can just sub it back into this equation. So I'm going to start with that equation again. I've used it once down here. I'm going to use it over here now. So I'm looking for the amount at time. I'm looking for AT this time. I have the amount at the beginning, which is 200 times e to the power of k, and I know k now, 1.0986. And the time is after 24 hours, as the question tells me. Right? So crunching through the numbers, and again, just be very careful that you do this first, because the calculator is a bit awkward. They're all a bit different, so you have to make sure you've done the multiplication first, on my calculator anyway, and then raise e to the power of that answer. Otherwise, just check through. Use your calculator a few times with the same question, and if you use different calculators, just check them out first, because the BODMAS works differently on different ones. Anyway, so once crunching through, we get 5.6 times 10 to the 13, which is the number of bacteria, which is a hell of a lot of bacteria. Okay, so I hope you found this video useful, interesting, and enlightening. I did try to kind of share the kind of understanding of where E comes from, and I think that's important to try and get your head around how the maths works, because if you want to use that maths in other scenarios and apply your skills broadly, which is what we want you to be able to do, then you should really be trying to get your head around the deeper thinking behind it. Now, proviso on this is that I'm not actually a mathematician. I'm a trained as an engineer, but this is me exploring the idea myself and how I think about it, and hopefully this inspires you to go ahead and do some research of yourself. And I'd love to see some student submitted videos where they can find E has a use, because I know there are many uses of E. Okay, E Eulers number. Alright then, so thanks for watching. I hope you enjoyed. Please comment, like, subscribe, share and all that business. See you later.